Hello guys, and welcome to my YouTube channel, A-Level Physics Redefined with Keith T. To start off, we're going to start off with October-November 2014 question paper 134 physics, and I'm going to be explaining it in depth, some of the questions that were asked and what you can do in order to answer those questions efficiently. And I'm going to post the paper down in the comment section below so that you can be able to access it and work it down on your own. So do check my description below, and I'll try to put timestamps so that you can be able to access different parts of the video and be able to go to a specific question that you want to answer. And if you do find value and you do find some of the questions really helpful, please do subscribe and hit the like button. So to start off, we'll start off with the first question, which is, when brakes are applied to a vehicle moving at a speed v, the distance d moved by the vehicle in coming to rest is given by the expression. Okay, so we've been given this expression, d is equals to kv squared, where k is a constant, and we've been asked to find the unit of k in SI base units. What does this mean? It means that, well, let's assume you have a car, right? You have a car that's moving, and as the car is moving, you suddenly apply the brakes. Maybe you see something in front, maybe an animal or something like that. So you've been asked, you have a certain equation that defines the distance that you move, and it's related to the speed that you have, and be asked to express k in SI base units. So what are you going to do? The first thing that you're going to do is going to make k the subject of formula. What are you going to do? So we're going to say k will be equal to d divided by v squared. And the units of d, we already know they are in meters, and the units of v squared, that will be meters per second squared. So this should give you m divided by m squared s to the power of -2. Now, the m and the m on top and bottom are going to cancel out, so you're left with 1 over m s to the power of -2, and this is going to give you m to the power of -1 and s to the power of 2, and that's going to be the answer. And the answer is going to be A. So that's very important, right? So whenever you're asked a question that relates to SI base units, you just want to make that thing the subject of the formula. Very important. Moving on to the next question, we've been asked which list contains one vector quantity and two scalar quantities. So the very most important thing about this question is understanding the two properties, which is the vector quantity as well as the scalar quantity aspect. Now, what does it mean? It means that, well, what is a vector quantity and what is a scalar quantity? A vector quantity is simply a quantity that is concerned about two things. That is the magnitude, right? So that's the first thing, the magnitude, okay? But as well as the magnitude, the second thing that we have is the direction. So in this case, the direction matters. Where are you going, right? Are you going from A to B? Are you going from B to C? The direction is very, very important whenever you're talking of vector quantities. But when you're talking of scalar quantities, the direction does not matter. What matters is only the magnitude. So for scalar quantities, however, what only matters, okay, what only matters is the magnitude, right? It's only the magnitude that matters and nothing else. So what are you going to do? Out of all the answers that you've been given, which one of those answers only contains two scalar quantities and one vector? That has to be C, where you have momentum, mass, and speed, because these two, okay, these two are scalar quantities and this one is a vector quantity. So the answer has to be C. Very important for you to have that in your mind. Moving to question number 3. In the circuit shown, we have an analog ammeter. So an ammeter, as you see on the screen, is basically a device that is used to measure current. What do? You connect it in a circuit, and it has now been recalibrated as a thermometer. So it's now going to be used to measure temperature. So a graph is shown to show how the resistance R of the thermistor changes with the temperature T. So we've been given that graph, and we've been asked which diagram could represent the temperature scale on the ammeter. So what are we going to do, guys? So you have to see that we have a relationship between the resistance and the temperature. So you're going to look at what exactly is happening to the resistance and what is happening to the temperature in order for you to be able to make a conclusion. So in this case, we know that the relationship which is true is that V, okay, we know that V is equivalent to IR. Okay, so that's a very, very important relationship that we need to know, because from this relationship, we can get a relationship between resistance and current. So from this relationship, we now know that the resistance is inversely proportional to the current. What does it mean? It means that if you increase the resistance, the current actually decreases. And if you look at this, for a very small temperature change, let's assume that this is just 20 degrees. For a very small temperature change, we have an abrupt drop in the resistance. That's a very big change in the resistance for just a small temperature change. So maybe we had a very high value, now we have a very, very low value. For another temperature change, we have very small now resistance change, because let's say we're at 80 here, we have a very small change. So it means that initially the resistance decreases rapidly, and if you're talking about current, it means that the current has to increase rapidly for a very small temperature change. So it means that if you look at your scale here, if you look at A has to be the correct answer, not B, not C or D. But why A? Because you need a very large increase in the current. Because remember, as the resistance decreases, the current has to increase. So you need a very large increase in the current, which is happening here, because if you have your meter over here, let's assume the meter deflects and the meter is now pointing over here. That's a very large increase, guys, because you have all that as your increase. But as you now move to this other direction, now you have very small increases, very small, very small, very small, which is happening as you move towards 100. So at first you need a very large temperature increase, but then you get a very small temperature a current increase as the temperature will begin to proceed. So the answer has to be A. Very important, guys. Okay, so in number 4, the diagram shows part of a thermometer. What is a thermometer? Well, it's an instrument that we use to measure temperature. And as you can see on the screen, that is the thermometer. And those are what we call the calibrations on a thermometer. How does the thermometer work? I'm very curious about how the thermometer works, because the thermometer has small divisions, which are 20, 21, 22, 23, 24. So in this case, our reading has to be 24 degrees Celsius, right? That goes without saying, that the reading has to be 24 degrees Celsius. So what's the difference here? The difference is in the uncertainty that are in those readings. What is the uncertainty in our 24 degrees Celsius? Well, it's very important for you to understand what we mean when we say uncertainty. What does it mean to say that we have an uncertainty that will be present? Well, the uncertainty refers to how unsure you are about a specific value. So let's assume you want to make a specific measurement. So you give yourself a room of error to say, I don't know the specific measurement, but I think with this amount of accuracy, I'm very sure that the true value lies in this range. What do I mean? Let's say you want to measure, let's say you have a table, right? You want to measure the length of that table. Then you tell me that, no, my length is 20. Just an example, you say it's 20 plus or minus 2. It means that you don't know the exact value, but you're uncertain. So you say, okay, I think it lies between 18 and 22. So it's 20 plus or minus 2. I don't know where specifically, but it has to lie within one of those two readings, right? So in the case of any instrument that you have, the uncertainty is going to be 1/2, okay? 1/2 of the smallest division. Okay, 1/2 of the smallest division. So you identify the smallest division and you halve that smallest division, and you'll be able to get the value of your temperature. So in this case, it's very important for you to say, what is the smallest division that you can get on a thermometer? Well, it has to be 1 degree Celsius, and half of that has to be 0.5. So 1/2, okay, the smallest reading is 1/2. So 1/2 of 1 should give you 0.5. That should be your uncertainty. What does it actually mean though? It means that if you go at 24, right? So let's assume this is your measurement, right? So it's something like this, so that you can better understand what's going on. Let's assume we have 24 here, right? And then let's assume we have 23, and then we have 25, right? We have something like this. What plus or minus 0.5 means, it means that if you take your answer to be 24, you're going to put this error bars somewhere here. Then you're going to say this is 0.5, right, but in the negative direction, and this will also be 0.5, but in the positive direction, right? So you say, I don't know if 24 is correct, but all I know is that in plus or minus 0.5, 24 has to lie in that range. So uncertain, so you say, and in 0.5, 24 has to lie in that region. So that has to be what the uncertainty is. So just remember, the key takeaway here, whenever you're given an instrument, 1/2 of the smallest division has to be the uncertainty that you're going to need. Get that, guys? So the answer is going to be D. Why? Because it's 0.5, which is half of the smallest division. Over to question number 5, we'll be given the resistance R of a resistor that is going to be determined. Now the current I that is flowing through the resistor and the potential difference V across it are measured. The results with the uncertainty I is shown. We're given I, we're given V, and we're given the value of R and is calculated to be 7.5 ohms. Okay, and we've been asked what is the uncertainty in this value of R. What do we do, guys? First, you write the equation. What do you know? We know that V, okay, is equivalent to IR. Okay, so we want to find the value of R. So the value of R will be equivalent to V divided by the value of I. But whenever we talk of uncertainties, we know that the uncertainty in R divided by R will be equal to the uncertainty in V divided by V plus the uncertainty in I divided by I. Now what this tells me is that the uncertainty in R will be equal to the uncertainty in V divided by V plus the uncertainty in I divided by I multiplied by the radius R. Very important relationship. So what does this tell me? If I have delta V, which is the uncertainty in the voltage, right, which is 0.5, so I should have 0.5 divided by 15.0 plus in I it should be 0.2 divided by 2.0, and if you multiply by the resistance that you have, in this case we have a resistance of, let me see, we have a resistance of 7.5, very important, we have a resistance of 7.5, and this should give you a value of, if I'm not mistaken, it should give you a value of plus or minus 1. So it should be plus or minus 1, which is going to be the answer that you're going to get, and it's going to be D. Very important. Whenever you're given an uncertainty question, always say fractional uncertainties will add, and they will give you the fractional uncertainty in the variable that you're going to need. And that only applies when you're either multiplying or when you're dividing. So very important, guys, for you to keep your head wrapped around those two facts. Okay, moving on to number 6, we've been given an experiment to determine the acceleration of free fall G, right? So we have a ball bearing, right, and it's held by an electromagnet. Now, when the current to the electromagnetic is switched off, so automatically as it's switched off, the clock starts, right? So you have something falling, and then as you switch off the clock, it starts to fall, and the ball bearing then falls. But after falling a specific distance h, the ball bearing strikes a switch and it stops the clock, right? And it measures the time t of the fall, which expression can be used to calculate the value of G. So I need you guys to just pause and try to work these questions out on yourself, unless you haven't otherwise, because with physics it's about trying to solve problems on your own and being able to think through the different questions that are going to be asked. So very important for you to develop that skill. So in this case, what do I know? I asked myself, what equation can I use? Well, I could use the equation S is equivalent to ut plus half gt squared, but the initial velocity is just going to be u. So this initial velocity is going to be u, meaning that the value of S would just be h, which is equivalent to 1/2 gt squared. So the value of g is going to be equivalent to 2h divided by t squared, and 2h divided by t squared is going to be d. Very important for you to be thinking about that. Move on to question number 7. We'll be given the diagram that shows the velocity time graph for a mass moving up and down on the end of a spring. So we have a spring, okay? As you can see, we have a spring, and we position a mass on that spring. Okay, what are we doing here? We want it to move up and down, up and down, up and down. But we want to find the velocity when it's at its lowest point of motion. Get this, guys. As it moves up, it's going to stop before it moves down, right? Otherwise, it's going to move up and reach the ceiling or something like that. So it's going to stop at a specific point. But when it stops, right, it's going to fall down, and it's going to have the highest speed when it's at the center. That is the equilibrium position. But it goes down, it falls and falls and falls and falls, and it stops at the bottom before it moves up. So you see a trend, zero velocity at the bottom, it rises up, fastest at the equilibrium, zero velocity at the top. So in this case, as it moves up, this is at the equilibrium, zero velocity at the top, it moves down, and zero velocity. Yes, the answer has to be D. Very important for you to keep these facts in mind. Move on to question number 8. I'm given a small ball that is released from rest on a smooth slope xy. So if that ball, and that ball moves down the slope along a smooth horizontal surface. Why do they say smooth? I always wonder why they say smooth. Well, if you're wondering like me, the word smooth refers to lack of friction. So in this case, whenever you see the Cambridge saying smooth, 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 it probably means that there is lack, okay, there is lack of friction. So I just want you to keep that in mind. Whenever you see the word smooth, just have that in mind. and rebounds inelastically. Inelastically means it's a collision where energy is not conserved. Momentum is, but the total energy is not conserved. That's something that we need to think about. Okay, then it moves back to y and comes to rest momentarily somewhere on xy, right? Okay, so which velocity time graph represents the motion of the ball? So as the ball falls, what's going to cause the acceleration of this ball? We have the weight mg, right? That is going to be acting down. Okay, and if we're to resolve this, we're going to get this component, right? And then let's say it's mg sine theta is going to be this component that's causing it to accelerate downwards. But guys, this component is going to remain constant. Mg sine theta is not going to change. Is theta of the slope going to change? No. Is the mass going to change? No. G change? No. So it means that the acceleration is going to remain constant. It's there, but it's constant. So it means that it's a line that's like this, is there, but it's a constant acceleration because the gradient of a velocity time graph represents acceleration. But when the ball reaches this point, right, when it reaches a point like this, okay, when it reaches this point, you realize that the mg is now acting down, meaning that the force is now acting down. But what's happening here? The ball is moving in this direction, right? So it means that the acceleration and the movement of the ball are no longer in the same direction. So the acceleration has to be 0, as we can see over here. But as this thing collides on the wall, it loses some of its energy. So it's going to have less kinetic energy, right, than before. So if it was moving very fast, it's now going to move very, very slow. But as it moves very slow, it will take a longer time to travel than it once did because it's now slower, right? So it's literally going to take a long time. So it means this distance, right, which represents where it's just on YZ, is going to be very long because it's now moving slower. It has lost its energy. Its kinetic energy has reduced. So it's going to travel very, very slowly until it reaches point Y. So it's going to have a longer thing like this, but it can't be D and it can't be B because, well, this and this are almost the same. But we're saying that the velocity has reduced, so it's going to take a longer time at a very slower velocity to reach that same distance. But if you look at this, the difference between A and C lies in this region, that is over here, right? In this region, it looks as if it's more steep, right? It's very steep than it once was here. That's a fallacy because it's false, right? Because think about this. The acceleration doesn't change. Mg sine theta, whether we're going up or down, doesn't change, right? The force is just going to remain the same, meaning that the acceleration should be the same on this graph. So the acceleration here, right? So the acceleration here on this graph and the acceleration on that graph should basically be the same. So the answer is going to be A, because in C, it's more steep, implying that the acceleration is greater, of which we don't see that happening. Okay, move on to question number 9. We'll be given a man who weighs 240 newtons on Mars, where the acceleration of free fall is 4 meters per second, and on the moon, G is 2 meters per second. Which statement is correct? Okay, so let's just write what we know, right? We've gone to Mars, right? And the acceleration of free fall is 4 meters per second, right? And we've gone to the moon, and the acceleration is going to be 2 meters per second. So how do we solve this problem? Which one is true? Well, we know that weight is going to be mass multiplied by G. Okay, so the mass of this guy is going to be the mass, right? So we have a man. Let's say the man is Rob, right? So Rob weighs 240 newtons when he's on Mars, right? So hi Rob. So he weighs 240 newtons when he's on Mars, and his mass is going to be 240. Okay, so his mass is going to be 240 divided by the acceleration on the moon itself, right? On Mars, which is divided by 4. That's going to give you 60 kilograms. So he weighs 60 kilograms. But when you go on the moon, what is his weight? Well, the weight on the moon is going to be the mass of the person multiplied by the value of G. The mass is 60 multiplied by 2. You're going to get 120 newtons. So the answer is going to be C. The men will weigh 120 newtons on the moon. Very exciting, right? You know, he gets to travel from Mars to the moon. Very exciting time for Rob. Okay, move on to question number 10. We'll be given a body that experiences a varying resultant force, causing its momentum to vary. Wait, what is momentum? Well, momentum is the product of mass and velocity. A body moves at a certain velocity and you multiply with its mass and you get its momentum. Okay, so at what point is the resultant force having the largest value? So you need to understand what specifically is the gradient of a momentum time graph. So we define force. Force is defined as the rate, okay, the rate of change right? So it's defined as the rate of change of momentum. Okay, rate of change of momentum. What does this mean? It means that we have a change in momentum. Okay, a change in momentum divided by a change in time. The time changes, the momentum changes. Big deal, right? So the gradient of a momentum time graph, so the gradient of this graph, right, represents the force, because force is the rate of change of momentum, basically. So the gradient of momentum time graph is going to represent force. So in other words, the question is saying, at which point do we have the greatest gradient? It can't be C, because if you look at C, the gradient has to be 0 at that specific point, because, well, at C, there is nothing that's going on. Okay, so if we were to look at here, something like this, the gradient is 0 at point C, at point A, almost 0, and then at point B, right, at point B, we have this particular gradient. Okay, so if we have a gradient, something like this, it's a very, very steep gradient, right? So let me redraw it so that you can be able to see it. And you see that it's a very, very steep gradient. So if we draw it like this, right? But if we look at D, right, with something like this, which is more steep, C or D? The answer has to be C. So meaning that the gradient at C is greater than the gradient that will be present at D. So the answer for question 10 has to be B. We have the steepest gradient, so the greatest resultant force. Okay, number 11, we've been given a golf ball. So, you know, if you played golf, or you've seen people play golf, or you know what golf is, it's played using a golf ball, right? The white ball, and that ball is dropped onto a hard surface from a height h1 and rebounds to a height h2. So the momentum of the ball changes. Or how does it change, and why does it change? Well, let's answer those questions. So if we have a hard surface like this, this is our hard surface. Okay, we have a ball, right? We have a golf ball like this, right? Okay, so this ball is going to fall down, right? So this ball is going to fall down, right? Like this. Okay, so it's going to fall down. It's going to fall from a height, right? h1. Okay, so this is our height h1, right? So basically this is our height h1, right? So as it falls down, it's going to rebound, right? But it's going to rebound and move to a height h2. We don't know what h2 is going to be, so let's just assume that if h2 is going to be somewhere, let's assume that h2, you know, is somewhere over here, right? Okay, so if you assume that h2 is somewhere over here, it means that as it's now moving up, right, it's going to reach this point h2. Okay, so we've established basically what's going on here is going to arrive at this point h2. We've established what's going to happen here. But there's an important fact that you need to know, guys. We need to know that the change in the kinetic energy will be equal to the change in the potential energy. Because the loss in potential energy from the ball down, okay, should be equal to the gain in potential as it moves up. So we have a loss in potential as it moves down, it gains kinetic, and that kinetic energy is lost as gravitational potential as it rises up. So in the first scenario, we know that our EK energy, which is half mv squared, will be equal to mgh1, right? So the m cancels, right? The m cancels, we're left with 1/2. Okay, so we're left with just v being the square root of 2gh1. So that's the first scenario. But if we look at the second scenario, it's basically going to be the same, right? The same conservation, the same formula that we basically use to find v. We just use the same thing. So in this case, we'll be saying 1/2. Okay, so in this case, we'll be saying 1/2. Again, m of v squared will be equivalent to, but this is now v2. Okay, so let's just say v0, like something like this, right? Okay, so this will be equivalent to mgh2, right? So the m cancel, so v0 will be equal to the square root of 2gh2. Okay, so we've established these two facts, but we know something here. We know something that we can actually establish. We know that if you think about it very carefully, the final momentum, so the change in momentum is going to be the final momentum minus the initial momentum. Okay. So we know that we have final momentum minus initial momentum, right? So the final momentum is going to be m, the final velocity v0, minus m, the initial velocity v. But we're going to define going down as a negative and up as positive. So it means that the first velocity is going to be negative, right? But the final velocity is going to be positive. And the final velocity is going to be m, okay, the square root of 2g h2, and then the initial velocity is going to be minus m, but it's going to be the square root of 2g h1. Okay, but now it's going to be minus because the velocity itself has a negative sign, right? Because that velocity has a negative sign, and it's very important for you to be able to put that negative sign. So end up with m, the square root of 2g h2, plus m, the square root of 2g h1, and the answer is going to be B. Very important, guys, for you to keep that in mind. Moving to question number 12, we've been given a sealed cylindrical still that can be situated below the surface of water. Okay, so we've been asked what is the origin of upthrust that acts on the can. Okay, so a long time ago, there was this guy named Archimedes, right? Archimedes, and as he was bathing, I don't know how he came up with the idea, but it's worth bathing. He literally discovered the concept of upthrust, right? We don't have time to go in detail. If you're very interested in Archimedes, you can look it up online, or you can look it up on YouTube, on Wikipedia. There are a lot of stories about Archimedes. And yeah, he ran in the streets. He was naked and he was bathing, shouting, "Eureka, Eureka, Eureka," right? So Archimedes had just discovered a problem that was troubling him for so long, right? So, and that's where he sort of described and coined the thoughts of, upthrust, Archimedes' principle, and all those stuff, right? So do check him out. So next time, be very careful in your bathing. You never know. Next time, you might discover one of the greatest, principles that we might know in physics, right? So for Archimedes, what we only need to know for now is that the water pressure, the difference in water pressure, gives you an upthrust, because we know that pressure is the force over an area, right? So there's a fight between two pressures. One of the pressure is acting up, and all the pressure is acting down. So if a force that will be acting down on here, right? And you have another force that will be acting up on that particular body because it's being compressed by water, right? But the pressure at the bottom will be greater than the pressure at the top, okay? Why? Simply because, well, at the bottom, we have a greater depth of water. So we literally have this whole thing as a depth of water, right? Something like this. This is our whole depth of water as compared to here. We only have this as our depth of water. So basically the upthrust is going to be greater. Sorry, the pressure is going to be greater at the bottom than at the top. So it means that if we have a force at the bottom greater than a force at the top, it probably implies that the force at the bottom is going to push the thing sort of upwards, and the force on the bottom is going to push it downwards, and there's going to be a fight. But the force at the bottom is bigger, it's going to win, and it's literally going to move up. So that up thrust that it gains is the force that is due to the differences in pressure. So the answer is going to be C. So one pressure is bigger than the other, and it causes an upthrust force. Very important. Okay, question 13, we've been given a cylinder of weight W that is on a smooth. Remember, the word smooth means there is no friction. Exactly. So the contact force of the slope on the cylinder, which is R, okay, and we have a thread which is attached to the surface of the cylinder, and the other end of the thread is fixed. Okay, so which diagram shows the cylinder in its equilibrium position? So in equilibrium, you need to learn two things when it comes to equilibrium. Number one, if forces are in equilibrium, the resultant force, very important guys, the resultant force, okay, is 0. What else do we need to know? The resultant torque has to be 0. Okay, so for this problem, we were just concerned with the resultant torque. Okay, but what is torque? We know that the torque is the force multiplied by the perpendicular distance from the line of action of the force to the pivot. Perpendicular distance. So if you have something like this, right? Basically, let's assume you have such a scenario, right? You have a scenario maybe like this, right? Okay, and what's going to happen is you're going to have a certain force that you're going to apply at that point, right? That's going to be acting down. So what you're interested in is this perpendicular distance from the line of action of the force to the pivot D, and then this force F, right? So your torque is literally going to be your force, right? So it's going to be your force F times your distance, which is going to be D. But if this D is 0, right, there can be a scenario where that D is 0. What does the scenario look like? So if you have the same scenario like this, right, but you have a scenario where the value of D is 0, meaning that the force is literally at the pivot, right? We're not going to have any torque because the distance is 0, right? So This whole fact gives us a situation where if forces intersect at a point, if all forces intersect at a point, the resulting torque has to be 0 because there won't be a perpendicular distance at the point of intersection. I don't know if it makes sense, right? So if all forces intersect at one point, as they do in C, probably means that the resultant force is going to be, the resultant torque is going to be 0. So that's a very big assumption that we can then use because we don't know R, we don't know the tension that is in that thread. Maybe they're big enough to combat the weight and big enough to oppose each other, and the forces are balanced, but in this case we're mainly concerned with the torque, and the answer is going to be C. So, if it doesn't make sense, please do comment and I can be able to respond and try to make it make sense for you. Please do utilize that. Okay, move on to question number 14. We'll be given a uniform meter rule of mass 100 grams that is supported by a pivot at the 40 centimeter mark and a string at the 100 centimeter mark. The string passes through a frictionless pulley, so this is our pulley, okay, very important, and carries a mass of 20 kilograms as shown. Okay, at each mass on the ruler, mass at 50 grams must be suspended so that the ruler balances. Okay, so the ruler has mass 100 grams, so we're going to go at the 50 centimeter mark, and this is where we're going to have the mass of the ruler acting down, okay, but mass, to transfer it into a force, is going to be 100 over 1000 times 9.81. So that's going to be the force acting here. Then on this side, we're going to have tension, right? So we're going to have tension here. Then we're going to have our tension somewhere like this, right? So this is going to be our tension. And for this force, we're going to have 20, right? 20 over 1000 times 9.81. Okay, so we have two forces, one clockwise, one anti-clockwise. Okay, so if you have seen a clock, as a clock moves in that direction, that's clockwise, but it moves in the opposite direction, that's anti-clockwise. So that's basically clockwise, anti-clockwise, right? So you're following the clock or you're opposing the clock, basically. So the summation, in this case, the summation of the clockwise forces must be equal to the summation of the anti-clockwise forces. Summation of clockwise forces must be equal to the summation of the anti-clockwise forces. So for the clockwise forces, what are we going to have? For the clockwise forces, we have this force acting down times a distance of 10, right? So we're going to have 100 over 1000 times 9.81 times 10 over 100. But in this case, we're literally just going to have, 20 over 1000 times the distance, which is 60 over 100 times 9.81. Right, times 9.81. So on this side, you're going to get 0.11772, but on this side, you're going to get 0. Okay, so you're going to get 0.0981. So you're going to get 0.0981. So it's a very, very important value for you to be considering. So once you have that specific value, look that there's a difference. So basically, you need to apply our force on this side so that everything balances, so that everything is basically the same. So since we have 0.091 here, we're going to have 0.0981. This is where we're going to apply our force, but it's 50 over 1000 times 9.81, but times our distance x, because we need to supply the clockwise moment because it's deficit, right? It's very small, so we need to supply clockwise moment. And this will be equal to 0.11772. Okay, so we have 50 over 1000 times 9.81 multiplied by x. Now this should be equal to 0.11772 minus 0.0981. Okay, so the value of x is just going to be that whole answer, 0.11772 minus 0.0981 divided by 50 over 1000 times 9.81. Right, so you're going to get a value of x that's going to give you about 0.04 centimeters. So I mean that you need to place your thing from 0.04 centimeters from the pivot. So it's going to be somewhere here. Okay, so it's going to be somewhere here, right? So it's 0.04, which is about 4 centimeters, right? So you need 4 centimeters here. So you basically need to place it on, this is going to be the 44 centimeter mark. So the answer is going to be C, 44 centimeters. Very important. Moving to question 15, we've been given a constant force F acting on a car of mass M, right? Moving up a slope through a distance S at a constant velocity V. The angle of the slope is alpha, which expression gives the efficiency of this process. Okay, so efficiency basically refers to you do something, right? Let's assume you're reading, right? As a student, you're reading trying to get good grades, right? That's the goal. Okay, so you put some energy, some effort in, right? You read, maybe have good techniques, right? Good usage of time, most probably. And your goal is to get very good results, right? So you have an energy input, you have a work input, right? Okay, but you get something out, right? This can be results, this can be quizzes or something that you do. So you have an energy out, but you have an energy in. So efficiency, you're sort of comparing how much did you put in versus how much did you get. For most students, they get very stressed. Maybe they put a lot of effort, but they don't get the grades that they want, right? So sorry, something like that. So it's now a matter of I've put in a lot of energy in, but do I get a lot of things out, right? So with efficiency, think about the same thing. What are you putting in and what are you getting out? What's your goal? So in this question, our goal is to raise it from point A, okay, as you see on that question, from point A to go to point B. Okay, so that's our goal. Okay, so we're going to raise its gravitational potential energy, right? So our formula is going to be our energy in, okay, so let's go, our energy out over, right, our energy in. Or efficiency can also be power in over power out, right? So our energy out is going to be our raise in this height, which is going to be mgh, our raise in the gravitational potential energy, but our work done is going to be this force multiplied by that distance. So we're going to get Fs, F times S, basically F times S. But in this situation, this value are here, right? This value that we want on the side, okay, this value, right, is going to be, since we have S in that direction, right, we basically want to find this difference, right, in that value. So basically want to find this, okay, this is something that we want to find, okay, but we know that that's going to be alpha. So the value of that distance that we're going to need is basically going to be S, right, S sine of alpha, right, because it's opposite over hypotenuse. The hypotenuse is S, and we want to find the opposite, so it's going to be S sine alpha. Okay, so we're going to have mgh, but now going to be mgs sine alpha divided by Fs. The S cancels, so we're going to be left with mg sine alpha divided by F. So the answer is going to be D. Move on, question number 16. We've been given two particles, particle X and particle Y, right? And after colliding, they move together as one large particle. How much kinetic energy is lost in the collision? So how much kinetic energy has been lost as the collision occurred? So guys, we have particle X and we have particle Y. So let's assume that this is a snooker ball, right? Let's assume particle X is a snooker ball and particle Y is a snooker ball. They have the same mass, but they have different velocity. So what do? We say that the momentum before, okay, we say that the momentum before is going to be equal to the momentum after. Okay, very important fact. So that's the first thing that you're just going to notice. The momentum before will be equal to the momentum after. But the momentum before is going to be mv, right? Because you just have the mass, z, or the snooker ball, which is going to be x, and it's going to move a certain distance, right? Okay, so the velocity, we assume that the initial velocity is going to be u, right? So let's assume that the initial velocity of this guy is going to be u. Okay, then if you look at the other one, they're going to join, so they're going to form one mass. So we're going to have twice the mass, so we're going to have 2m. Okay, and then the final velocity is just going to be v for both of the guys, right? So just going to be v. So it means that the speed of x, the initial one is u, but the speed of them both after the collision. So after collision, they join together, right? So this is before, after collision. So this one just, decides to join the other one. So they join forces. And they're like, let's chill, let's stick together, and let's form one particle and let's roll together, let's move, right? So they're going to be one particle with one velocity. So we're going to treat them as one particle, but with masses added up together. So the value of v is going to be u over 2 from that expression. So you can sort of look at the difference in kinetic energy before and kinetic energy after and start to see what has been the change, right? So it's going to be, so the change in kinetic energy is going to be final kinetic energy minus the initial, minus the initial kinetic energy. So the final kinetic energy is going to be equivalent to 1/2 mv squared. The initial kinetic energy, again, is going to be equivalent to 1/2 mv squared. Okay, but in this case, it's going to be 1/2. Is our mass changing? No, the mass is still m. Our velocity is u squared. Minus, in this case, we have 1/2. But our mass is actually changed, right? So we have 1/2, but our mass is now 2m. And the velocity is now u over 2 squared. So we're going to have 1/2, okay, mu squared. In this case, it's going to be 1/4. 2 and 2 cancel. So we're going to left with 1/4 mu squared, right? So 1/2 subtract, okay, 1/4. So you're basically going to get 1/4 mu squared, right? But the initial velocity is going to be ek, right? So the initial velocity is going to be ek. But we can split 1/4 into 1/2 times 1/2, okay, mu squared. So basically, it's going to be 1/2 of ek, or in simpler terms, ek divided by 2. And the answer is going to be C. Very important, guys. Moving to question 17. We've been given a box of weight 30 resting on a ramp, okay, that is at an angle of 30 degrees. Okay, I don't know who decided to leave, a box on a ramp, but, it's just going to slide down, and then it's going to fall a distance of 8 meters, right? So you want to find the kinetic energy of the box after falling through this distance. So what's happening, guys? What's happening is that we have gravitational potential energy. Okay, what's happening is that we know that the loss, okay, we know that the loss in the gravitational potential energy is equivalent to the gain in the kinetic energy plus the work that will be done, okay, that will be done against, right, that will be done against friction. Okay, so the loss in gravitational potential energy is going to be equal to that, okay? So the loss in gravitational energy is going to be mgh. That's going to be the gain in kinetic energy, okay? That's what we want to actually find. But the work done is going to be this distance, right? So we have a particular distance. We are moving from here, right, all the way down, right, to this point, from that point to that point. So in this case, it's going to be, that's the hypotenuse. So it's going to be 8, okay, 8 over sine 30. So this distance is going to be 8 because it's the hypotenuse, right? So it's opposite over the angle, 8 over sine 30, and that's basically going to be equivalent to 16. So here we're going to have 10 multiplied by 16. But on the MGH, we have 30 multiplied by 8. So that's going to be equal to our delta EK plus 160. So our delta EK is going to be equal to 30 times 8 is 240. You subtract 160, you end up with 80. So the answer is going to be A. Very important, guys. Move on to question 18. Okay, we have a little bit of an electric field situation going on here, and we no longer do electric fields. If you're currently doing AS, for the examinations from 2022, our electric fields were removed from the syllabus, so we'll not be covering question 18. But we will be covering question 19 though, right? So that's great. So a van driver adjusts the force on a van's brake. So we have a van, right, that's traveling at a constant speed down a hill from P to Q. The magnitude of the change in the van's kinetic energy is delta EK, and the magnitude of the gravitational potential energy is delta EP. Which statement is correct? Guys, this is a trick question. They always like to trick people. Get this. The change in kinetic energy is 0 because you're traveling at a constant speed, right? Is your speed changing? No. Is your mass changing? No. So your kinetic energy will be equal to 0. Guys, always remember this. This is a very important one. The kinetic energy will always be 0 if you're not changing. Whenever you see the word constant speed, it means that the kinetic energy is going to be 0. Very important. Okay, moving to question 20. The atmospheric pressure at sea level has a value of 100 kilopascals. Okay, very important. And the density of seawater is 1,200. At which depth in the sea would the total pressure be 110? So we have an ocean, right? We have a sea, a big sea. And if you look at the sea, right, at the sea level, we have an atmospheric pressure of 100 kilopascals. And we want to find at which depth we're going to have a total pressure of 110 pascals. Okay, so basically, since that is our sea, okay, something like this. The pressure here is going to be 110. So the pressure here is going to be 100. Okay, so if we have a specific point in this whole thing where the pressure is going to be 110, you probably know what this means, right? So we're going to have a pressure of 110. So it means that the difference in the pressure, right, is literally going to be 10 kilopascals. So the difference in the pressure is just going to be 10 kilopascals. And we can use that because that's caused by rho GH. And we have that volume, right? So we know that rho GH will be equivalent to our pressure, which will be equivalent to 10,000. So the value The value of H, which will be equal to 10,000 divided by rho times the value of G. So it's going to be 10,000 divided by 1,020 times 9.81. Yes, it's going to give you 1.0 meters, and your answer is going to be so it's very important for you to be just keeping those things in mind whenever you're working these questions out. Well, question number 22, we've been given two liquids, okay, P and Q, which do not mix, okay. So the liquids are in equilibrium in an open U-tube, and we've been asked what is the ratio of the density of P to the density of Q. So what do we know? We know that if we have this point, we're going to have the atmospheric pressure, right? The pressure of the atmosphere here, and we're going to have the pressure of the atmosphere here. So the pressure of the atmosphere plus the pressure of P will be equal to the pressure of the atmosphere plus the pressure of Q. Since you have the pressure of the atmosphere on both sides, they cancel out, and you'll be left with the pressure of P, which will be equal to the pressure of Q. Okay, so basically that's what you've established at this point A. Right, so that point A, we know that pressure is rho. Okay, so pressure is rho G, right? So it's rho P, G, H, P, which would be equal to rho Q, G, H, Q. Okay, fairly simple. So the density of P divided by the density of Q is approximately equal to the height of Q divided by the height of P. But the height of Q is X, and the height of P is 2X, so you're going to get 1/2, and the answer is going to be A. Very important, guys. Move on to question 23. What is meant by the ultimate tensile stress of a material? The ultimate tensile stress of a material. So basically, there's the maximum force, right, from stress. There's the maximum force per unit cross-sectional area supplied before a material actually breaks. So the answer is going to be C. So the maximum stretching force that you apply before a material actually breaks is what you call the tensile stress. Okay, move on to question number 24. The diagram shows the behavior of a sample of a metal when it is stretched until it starts to undergo plastic deformation. Okay, what is the total work done in stretching the sample from 12 millimeters in extension to from 0 to 12 millimeters in extension? Sorry. Okay, so we've been asked to simplify. Okay, so we've been asked to simplify the calculation by treating xy as a curve. So we're going to treat xy. So moving from here to here, so we're going to treat this as a straight line. So that curve, sorry, we're going to treat that curve as a straight line. So basically, we're going to have two shapes, shape A, and then we're going to have shape B. So what are we going to do? We're going to say the total work done will be equal to, okay, the area of A plus the area of B. Very important, guys, for you to conceptualize these things in a way that you can understand and comprehend. So the area of A is going to be 1/2 base times height plus 1/2 A plus B multiplied by H. Okay, so that's going to be 1/2. The base is going to be 10 basically. So 10 over 100 times 10, which is 1,000, times 500. Okay, so if we add the other one, it's going to be 1/2. Your A is going to be 500, and then the other one is going to be 550. Then the difference, which is this one, is going to be 2. So it's going to be times 2 over 1,000, right? And if you compute this on your calculator, right, you're basically going to get 3.55 meters per millimeter. Sorry, in this case, joules. Sorry. And if you simplify that, you're going to get 3.55 joules. So that's very important for you to be able to think of that and conceptualize that in a way that you can be able to understand. Very important. Move on to the next question. We've been given two springs, one with a spring constant K1, which is equivalent to 4. The other one with a spring constant K2, which is equivalent to 2. And we've been asked what is the total extension of the springs when supporting a load of 80 newtons. Okay, so you know that F is going to be equivalent to KE. So E is going to be F divided by the value of K. But these two things are in what we call series. Okay, so there's a very important thing that you're going to have to master. For springs in series, right? So whenever springs are in series, that means they're joined one after the other, right? So in a normal series that you have episode 1, episode 2, episode 3, but so you can't go to episode 2 without seeing episode 1. So in springs with series, you can't go to the next spring without looking at the spring before. So sort of like that sort of basic scenario, like they're one after the other. Okay, so when you're making calculations for the spring, you need F. So F is going to be the same for both of them, right? Because, well, assuming that this spring has a negligible mass, right? This is going to feel, right, 80 newtons. But this is also going to feel 80 newtons. So the force basically remains the same. But what's different is the extensions, though. The total extension for springs in series, right? The total extension is going to be the extension of A, right? Let's assume that this is A, then this is B, right? So it's going to be the total extension of A plus the extension of B. But we know that F, right? We know that F is equivalent to Kx. Therefore, X will be equivalent to F divided by K. So we're going to have F divided by Kt equivalent to F divided by Ka plus F divided by Kb. So if we factor out F, we'll be left with 1. Okay, we'll be left with 1 over Kt being equivalent to 1 over Ka plus 1 over Kb. So the value of Kt in this case, so the value of our total K, right? So the value for total K will be equivalent to, in this case, it's going to be 1 over 2. We have 2 and 4, right? So it's going to be 1 over 2 plus 1 over 4 to the power of -1, because 1 over K plus is the power of -1, and you cross the other side, it becomes a -1, right? So in this case, you're going to get 4 over 3 kilonewtons, right? So it's 4 over 3 kilonewtons per meter. Very important, guys, for you to keep that. So we now have F and we now have K. So we can then find E, just 80 over 4 over 3 times 1000. That's basically going to give you an extension of 6. Wow. So, that's it with physics, right? So it's going to be 0.06, and that's basically going to be 6 centimeters. So you had to use two facts. For springs in series, the total extension is the same. So find the total value of K. And it is the fact that for Hooke's law, right, invented by Robert Hooke, F will be equivalent to Kx. So the force that you have will be equivalent to the extension that you have, right? So something like that, as you'll be making the calculation. Okay. For question 26, which statement about waves is correct? Okay, so we know this one, right? So all electromagnetic waves travel at the same speed in a vacuum. So the answer has to be A. Longitudinal waves cannot be polarized because they oscillate perpendicular to the direction, right? So it's like they're parallel. So it's parallel. And for polarization, we need perpendicular things so that we can restrict the vibrations. But we can't do that for longitudinal waves, right? Amplitude is not really directly proportional to the energy transferred. And the frequency of infrared is not greater than the frequency of ultraviolet. So basically, but we know that for a fact that all electromagnetic waves travel at the same speed in a vacuum. That's 3.0 times 10 to the power of 8. You know how light travels from the sun until it reaches Earth? That is at the same speed, which is 3 times 10 to the power of 8, right? Moving to question 27, we've been given the variation of distance x of the intensity I along a stationary sound wave in air as shown by the following graph. The speed in air is 340 meters per second, and we've been asked what is the frequency of the sound wave. What do we know? Well, basically, we know that V is going to be equivalent to F lambda. So the frequency is going to be equivalent to V divided by lambda, and the value of V is 340 divided by the value of lambda. Right. Okay, but on this graph, an intensity amplitude graph, intensity is maximum because intensity is related to the amplitude. Intensity is maximum at an antinode, right? An antinode is where you have the maximum intensity. And we know that this is an antinode and that is an antinode because we have the highest intensity. And minima is a node, we have the lowest intensity. And we know that the distance from an antinode to an antinode is going to be 1/2 lambda, right? So we have 10 centimeters here, and that's equivalent to half lambda. So lambda will be equivalent to 2 times that. So here we're going to have 340 divided by 2 times 20.0 divided by 100, and that's going to give you, so for number 27, that's going to give you, roughly 1,700 hertz, and the answer is going to be A. Okay, 1,700 hertz, the answer is going to be A. Very important, guys, for you to be thinking of this stuff. Okay, so plane waves in a ripple tank pass through a gap. So we have a ripple tank and we have diffraction occurring. So diffraction, we have a small gap and light spreads into the, the observable. And as it spreads into different regions, right, the wavelength remains the same. Well, why do I say this? If you look at the graph, this wavelength, right, is literally just the same. The wavelength has remained the same. And if the wavelength remains the same, the frequency is going to remain the same. And if the frequency remains the same, because we have the same wavelength, we have the same frequency, the velocity is going to also remain the same. So the only thing that changes really when you have diffraction occurring is just going to be the amplitude. So the answer is going to be C. The amplitude is the only thing that is going to change whenever diffraction begins to occur. That's very important for you to be able to think and be able to conceptualize when you're working out. Okay. With question 29, you'll be given an organ pipe. If you haven't seen an organ pipe, or you're seeing it right now on the screen, right? So it's of length L and it's open on both ends, right? So it's open on both ends. So what does it mean? It means that we're going to have something like this, right? Bear with me, guys. Okay, so we're going to have an antinode here. And we're going to have another antinode that will be on that direction. Okay, so like I've said, the distance from an antinode to an antinode is going to be 1/2 lambda, guys, 1/2 lambda. Okay, so what is the lowest frequency that we can ever get? Well, frequency is going to be equivalent to V divided by lambda, right? V divided by lambda. But this distance, guys, is going to be equivalent to L. So this distance, okay, is going to be equivalent to L. So this distance is going to be equivalent to L, right? So basically, we're going to have 1 after. So, but 1/2 lambda is going to be equivalent to L. So lambda will be equivalent to 2L. Therefore, F will be equivalent to V divided by 2L. Right, so basically, this is going to be the calculation for you to literally just find the frequency. Okay, so once you have that expression, look for the answer, which gives you that, and that's going to be C. Very important. Then question 30, we're given an interference fringe that is produced on a screen by double slit interference experiment using light of wavelength 600 nanometers. So that's the double slit experiment, as you can see on the screen. And the fringe separation is 4 millimeters, and the separation of the slits is 0.60 millimeters. So there's a relationship that you're supposed to know for AS level physics. You're supposed to know this definition by heart, guys. So we know that lambda is going to be equivalent to AX divided by D. So the value of D is going to be equivalent to AX divided by lambda. The value of A is basically the separation of the slits, which is 0.60 times 10 to the power of negative 3, multiplied by the value of X, which is 4.0 times 10 to the power of negative 3. We divide by the lambda, right? Lambda, which is our wavelength, which is going to be 600 times 10 to the power of negative 9. And we're going to get a value of D. Based on that is going to be the distance between the double slit and the screen, right? So we're going to have a specific distance, and that distance is going to be 4.0, right? Based off my calculation, it's going to be 4.0 meters. So whenever you think about interference fringes and all the stuff, we're going to do more questions, right? But just be thinking in the back of your mind, lambda is equivalent to AX over D. It's like the double slit experiment, right? Knowing that D sine theta is going to n lambda is a fact. You're supposed to have that solidified in your head whenever you're working the double slit experiment. So basically, those are some of the things that you're supposed to just know as a student and be able to conceptualize and be able to understand whenever you'll be doing and working out calculations. Very important. Okay, question 31, we've been given a region of unbalanced charge that are produced inside a cloud as shown. Yeah, so that's basically electric fields. They're out of our syllabus if you're doing AS after 2022. Question 32 again, these are electric fields. They're also out of our syllabus. So we'll start with question 33. So for question 33, you've been given a metal wire of length 0.50 meters and as a resistance of 12. What is the resistance of a wire of length 2 meters and made of the same material? So same material means same density, same resistivity, but half the diameter. Okay, so we're going to calculate it here. So we know that rho R is equal to rho L divided by A. Right, so the value of R okay, so we know that R is going to be equivalent to the resistivity multiplied by the length multiplied by the area. And we say that the resistivity in this case is going to be equivalent to R A divided by L, right? But it's literally just going to remain constant. Okay. So rho in this case is going to be equivalent to, our resistance is going to be 12 times pi d squared divided by 4 divided by the length of that, which is going to be 0.50. Based on our question, it's going to be 0.50. Okay, so rho is going to be equivalent to 4 and 12 give you 3 pi d squared divided by 1/2. So you're going to get a rho which is equivalent to 6 pi d squared, right? So this is the first row. So this is for the first first wire. Okay, so for the first wire, you're going to get this value of rho, and for the second wire, okay, so let's do for the second wire, somewhere here. For the second wire, the value of R again is going to be equivalent to rho L divided by A. Your rho is going to be equivalent to R A over L, but it's constant. So it means that this answer, guess what, it's going to apply here. So we're going to have 6 pi d squared. I hope you're following, guys. Going to be equivalent to R times, we want to find R, right? Pi d over 2, okay, all of that squared, divided by 4. Divided by 4, divided by a length. In this case, we have 2, a length of 2 meters. So we have 6 pi d squared, that is equivalent to R pi, right? D squared divided by 4 times 4 is 16 divided by 2. So you have 12 pi d squared being equivalent to R pi d squared divided by 16. And if we multiply 12, right, 12 by 16, okay, we're going to get 192. So we're going to get 192 pi d squared equivalent to pi d squared R. Okay, so on to question 34. A student found 2 unmarked resistors. To determine the resistance of the resistors, the circuit below was set up. The resistors were connected in turn between P and Q. Okay, so he's just going to try out some new things. I'm a very curious guy, right? So as you can see from the question, the EMF remained constant, and this is so because if you look at 1.5, it's also 1.5, meaning that the EMF actually remained constant, and the first row has to be the EMF because, well, the EMF is the only thing that remained constant in this whole scenario, and this means that B and C are going to be wrong answers. And then if we look at we'll be left with A and D, and if determine which one of those two is wrong or which one of those two is correct. So if we're to start with A, and with A we're given 46 on top and we're given 100 on the bottom, then we're given 28 on the top and 14 on the bottom, and for A we're assuming that I is current. Now that current is inversely proportional to resistance, and what this means is as the current is going to increase, let's assume the correct answer is A, the current is going to increase, the resistance therefore has to decrease from that whole experiment, right? Which is very true, that the resistance is going to decrease, because we know that the bigger the resistance, the bigger the amount of voltage that you're going to get, meaning that you have to have a very big voltage for you to have a very big resistance. So it doesn't make sense. If current is inversely proportional to the resistance, if the resistance, let's assume the correct answer is going to be A, if the current is going to increase and the resistance is going to decrease, therefore the resistance should have increased, right, for us to have a bigger voltage drop. But D has to be correct because the resistance has increased, and if the resistance is increased, the current is going to decrease. And if the current is going to decrease, we know that now the voltage also in that same regard, the voltage also has to increase, because like I've said, the resistance has increased, the voltage will also increase, and the current would have decreased. So the correct answer has to be D. Very important, guys. If anything is unclear, please do put it in the comment section, but I hope that makes sense. Move on to the next question. We'll be given a potential divider that consists of resistors of resistance R1 and R2 that are connected in series across a source of potential difference V0. So we're given the potential difference across R1 to be V out, and we want to find the change that will increase the value of the voltage out. So how voltage works is very exciting and very interesting, because if we look at it, the bigger the resistance that you have, so basically the bigger the resistance. Okay, as I write down, just reflect on these facts. The bigger the resistance that you have, inversely, the bigger the potential, drop or the potential difference, right? Okay, so the bigger the resistance that you have, the bigger the potential that you're going to need. So if you have a big thing, current is going to need a bigger resistance in order for it to travel through a specific point, because there's literally a bigger resistance for it to move. So it's going to need a bigger potential drop because there's a bigger resistance that is present. So R1, if we double R1 and if we halve R2, we have the biggest potential drop across R1 because we have the biggest resistance. You have a big resistance, so you're going to need a bigger potential difference in order for you to drop, or in order for you to experience a potential drop across that specific point. So very important for you to be thinking of that. One question, given an extension lead that is used to connect a 240 volts electrical supply to a heater as shown. So we have an extension lead with a power source and we have that whole circuit shown. And we have a voltmeter that measures the potential difference as 216 and an ammeter that measures the current as 7.7. And we've been asked to find the total resistance of the extension lead. Now guys, I want you to remember this as a very, very important fact, because if you look at this question, essentially what you can do is you can redraw this diagram. So if you redraw, you have something that looks like this, basically. So when you have something that looks like this, right, it means that if you have this particular region, that's representing your power source, right? Because I've redrawn it, that is now representing my power source, and this is my heater, and these two are my extension lead. The first extension lead is here, then the second extension lead is over here. So you have a power source that is over here. So current will start moving here, passes through that extension lead, gets to the heater, then moves through to the other extension lead. But we know the equation V is equals to IR, right? We know the equation V is equals to IR, which would be over here. Okay, so how can we find the resistance? Well, the resistance will be equivalent to the potential difference divided by the current. But we have 250 at this power supply. We have 250 over here, but this one gets 214. So it means that the difference, right, the difference of 240 and 216, which is 24, will be the amount of potential difference that it uses to go over the two resistors, the two lead resistors. Okay, and the current is basically like 7.7. So basically we're going to have 7.7 below there, and we divide the two, we're going to have 3.1. So 3.1 is going to end up being our total resistance. So remember, redraw. Whenever you see a complicated circuit, just try to redraw into something that you're familiar with, something that you know, and then you try to make sense of that, and then try to figure out how you can be able to make sense of it, and then do it in your own way. So the answer has to be A. But we're going to 37. In the circuit shown, the ammeters have negligible resistance and the voltmeters have infinite resistance. So infinite resistance, underline that, it means that the resistance is so big that no current flows through the voltmeters, and that's very good, right? Otherwise the voltmeter will not do its job of just measuring, rather it will now take current from the circuit, and we don't want that at all. We want it to measure, not necessarily take something away. So what we do here, is we redraw our diagram like this, right? So by redrawing, it means that we have our power supply here. This is our power supply, and I just gave it 10 volts just for convention, so that we can be able to see what's going on. And we have two resistors, one with 6 and then the other one with 3. Here we have one with 2 and then the other one with 2. So we can basically find the total resistance across this whole situation, by that whole setup, and the total resistance will be 1 over 3 plus 1 over 6, or product over sum 6 times 3 over 6 plus 3, right? So it's product over sum 6 times 3 over 6 plus 3 right here. So you get an answer, a total resistance of 2. Okay, then for the other one, you're going to have 2 times 2 over 2 plus 2. You're going to get a total resistance of 1. Okay, so you have a resistance of 2 over there, resistance of 1 over there. So we want to find the potential difference across the first one. So across the first one, it will be 2 over 3 multiplied by 10, right? And you're going to get a value of 6.667. Okay, that's going to be the potential drop across these two guys, right? But for the other one, it's going to be 1/3, just 1/3 of 10. That's going to be 3.333 volts, meaning that this guy gets 3, roughly 3, then these guys get roughly 7, right? And from this case, automatically V1 has to be greater than V2. So your answer can either be A or C. B or D is wrong. You see, guys, working with calculations make your lives so much easier whenever you're working out these different calculations. So
Once you have the potential difference, how do you find the current across the 3 ohm resistor? Well, it's fairly simple because you know that V is equivalent to IR. So the value of I will just be equal to value of V over R. So your value of I, your V, you have it because when things are in parallel, they have the same potential difference, because current, when it arrives here, it has a choice. It has 6 volts, 6.67 volts, of course, and there's a choice to go up or go down. So current is going to move, and as current moves, it's going to move either up or down, and we're therefore going to be able to make different calculations based on that specific assumption. That's very, very important for us to be thinking about that. Okay, and then for the other one, it's going to be 3.333 divided by 2, and we're going to get 1.60. For the other one, we're going to get 2.22. So automatically, I1 has to be greater than I2, and the answer has to be A. So remember, guys, you just have to look at the situation, what has been arranged, and what can you do in order to change the setup so that it can be able to make sense. Just kind of have that in mind. Over on question 38, we've been given the nucleus of a radioactive isotope. So we've moved to atomic physics, where we delve into the atom of a nucleus and we try to understand the different particles that exist, the protons, the neutrons, the leptons, the quarks, and all those fundamental particles that makes atoms special. So normally this topic comes with about 3 or 4 questions. In this case, we have 38, 39, and 40, but we won't do 40 because it's covering on electric and magnetic fields, and they're no longer done in AS if you're doing the syllabus from 2022. I mean, I assume you are, so you won't be worrying about electric fields in AS. You worry about them in A2, so you don't have to worry much about how they're calculated and how the calculations are made. But for this case, we only have question 38 and question 39. Okay, so let's start with 38. We've been given the nucleus of a radioactive isotope that emits an alpha particle. So when a radioactive decay occurs, it emits alpha particles either because it's unstable, so it's going to emit some specific particles, alpha particles, beta particles. Specific particles are emitted during the process of radioactive decay. So in this case, we want to assume we have a radioactive isotope of 20 and 10, as you can see over here. Okay, if you assume that we have a radioactive isotope with 20, right, and 10, something like this, and it's going to undergo alpha decay. So if it undergoes alpha decay, right, it's going to form a new isotope, right? So if we have 20, it's going to form 4 and 2, right, like this, plus, but if we lose 20, we're left with 16. If we lose 2, we'll be left with 8, right? Let's just say it's Y. So what we form is a daughter, right? A parent gives a daughter, right? Physics. Okay, so that daughter is going to undergo beta minus decay, and beta minus decay, it emits a beta particle with a -1 charge, and to compensate for that, a proton has to be added, has to be converted from a neutron to a proton, right? So we have 9 protons here, so proton number becomes 9, and that daughter emits another beta minus particle. So that daughter is going to emit another beta minus particle, as you can see over here, and as that daughter emits a beta minus particle, it's going to shift 16, 10, then we're going to have M, right? But if you compare these two guys, what do you see that's similar, right? If you compare these two guys, let's take them aside, right? We have this first one, okay? Then we have this other one that is over here, right? I want you to look at what exactly is similar between these two guys. Well, if you look at it, this one has 10, right? This one has 10 protons, and this one has 10 protons, right? So 10 protons here, 10 protons here. Very exciting. But this one has 10 neutrons, right? And this one has 6 neutrons. The proton number is the same, but the neutron number is different. Well, what are those? Those are isotopes, my friends, because an isotope basically has the same number of protons, but different number of neutrons. So basically, X and M, they are different. So X, the first final nuclide will be an isotope of the original element. And for question 39, we have the conservation of charge, you have the conservation of momentum. In this case, we're going to have the conservation of nucleon number. Okay, so in this case, we have 238, right? Then we have 92 of U plus 4 and 2 of HE. That's forming 241 and 94 of PU plus X, right? So basically, we have this situation where we have these different things that are being formed, right? And if we look at them, right, what exactly is different? Right? Let's analyze the situation. Before, right, what was our atomic number? We had 92 plus 2, that's going to be 94. Then after, what did we have? We had 94 plus what? For us to get 94, it has to be plus 0, right? So basically, we need a 0 here in order for us to have something. So we need a 0, So we're going to need a 0 over there. But if you look at those up, the nuclear numbers, we have 238, we have 4. And if you add these two up, so we have 238 plus 4, is going to give you 242. But on the other side, we have 241 plus what? Plus what? What do we need to add in order for these things to be balanced? Plus what? Right? Basically, since we have 242, we have 241, we're basically just going to need 1. Right? We're going to need 1 here, so we're going to put 1 here. So basically, x, we have 1 and 0, has a nuclear number, right? It has a nuclear number of 1, but it also has a proton number of 0. Nuclear number 1, proton number 0, that is, my friends, a neutron. So we're done. Question 40, like I said, is electric fields, and we will not be covering that. So basically, that's a physics paper 1. What you're going to do is you're going to try to understand different questions, and I highly recommend that you work these questions on your own, get good practice of how these questions are worked out, and try to get a better understanding of how you can be able to apply these questions in different situations, different scenarios, and then everything should be fine, and you should be able to calculate this situation. Thank you guys for watching, and I'll see you in the next one.